What if I told you that swapping our Milky Way with just one specific galaxy would transform every night on Earth into a brilliant stellar showcase? That's the reality of living in Andromeda, our nearest galactic neighbor. This massive spiral galaxy contains over 1 trillion stars compared to our Milky Way's modest 400 billion, creating a night sky packed with starlight beyond anything we've ever experienced. But here's the flip side that comes with all that cosmic beauty. More stars mean more stellar deaths, and more stellar deaths mean more supernovas exploding throughout the galaxy. Each of these cosmic explosions sends waves of high-energy radiation racing through space, and Earth would sit right in the middle of this stellar violence. The sheer scale of Andromeda means we're not just talking about a prettier night sky. Living in Andromeda's stellar neighborhood. We're talking about moving into a galaxy that spans 220,000 light-years from edge to edge, which makes our Milky Way look like a compact car parked next to a freight train. While we're sitting pretty with about 400 billion stars in our galaxy, Andromeda houses over 1 trillion stars crammed into that massive space. That's more than double the stellar population density, and every single one of those extra stars would fundamentally change what Earth experiences on a daily basis. Step outside on any clear night in Andromeda, and you'd witness something that would make our current night sky look pathetic by comparison. The stellar density would be roughly twice what we see now, pushing the visible magnitude limit far beyond our current 6th magnitude threshold. Instead of the few thousand stars visible to the naked eye from Earth's surface, you'd see tens of thousands scattered across the sky like someone spilled diamonds on black velvet. The familiar patterns we've used for navigation and storytelling for thousands of years would vanish completely, replaced by entirely new stellar arrangements that follow Andromeda's different spiral arm structure. But here's where things get interesting in a terrifying way. All those extra stars aren't just pretty lights hanging in space for our viewing pleasure. They're cosmic time bombs, each one destined to die in spectacular fashion. Studies show Andromeda's supernova rate could be 1.5 times higher than ours, which means more stellar deaths and more high-energy radiation events. The increased stellar population creates a galaxy where cosmic violence happens at a much higher frequency than what we're used to in our relatively quiet Milky Way neighborhood. Right now, we're still in the safe zone of this galactic swap scenario, but the real problems are just getting started. The fundamental mechanics of how our solar system moves through space would change dramatically once we factor in Andromeda's different structure and gravitational environment. Our galactic year, the time it takes our solar system to complete one orbit around the galactic center, would stretch from 225 million years to roughly 500 million years. This massive change happens because Andromeda's larger diameter means our solar system would sit much farther from the galactic center, requiring more time to complete each orbital cycle. Earth's geological timescales would need complete recalibration, with major evolutionary periods and extinction events spaced across entirely different cosmic rhythms. Andromeda's spiral arms would subject our solar system to gravitational influences we've never experienced before. The galaxy's massive dark matter halo, which weighs approximately 1.5 trillion solar masses compared to our Milky Way's 1 trillion solar mass halo, would create stronger gravitational gradients throughout the galactic disk. Our solar system would experience different tidal forces as it moves through Andromeda's spiral arms, potentially affecting the stability of planetary orbits over very long timescales. The interstellar medium surrounding our solar system would become significantly more turbulent due to stellar winds from Andromeda's enormous population of red giant stars. These aging stellar behemoths constantly shed their outer layers into space, creating streams of hot gas and charged particles that flow between star systems. Our solar system would encounter these stellar wind streams more frequently, creating additional pressure on our heliosphere, and potentially compressing the protective bubble that shields us from galactic cosmic rays. Any future space missions attempting to navigate beyond our solar system would face complete chaos. The star patterns that form the backbone of celestial navigation would be totally scrambled, with familiar reference points like Polaris and the Southern Cross replaced by entirely different stellar configurations. Spacecraft would need to rely heavily on internal navigation systems and radio beacons, since using stars for directional reference would require completely rewriting every navigation protocol ever developed. Andromeda's denser stellar environment raises the odds of supernova hits and comet dislodgements by a factor of 2. The increased stellar density would create more frequent gravitational interactions between passing stars and the outer regions of our solar system. These close encounters, while still extremely rare on human timescales, would occur roughly 2.5 times more often than in our current galactic environment. Each passing star would exert gravitational tugs on objects in the Oort cloud, the spherical shell of icy bodies that extends nearly 1 light-year from our Sun. The Oort cloud contains trillions of potential comets, most of which remain frozen in stable orbits at the very edge of our solar system's gravitational influence. However, when passing stars disturb this delicate balance, they can nudge these icy bodies toward the inner solar system, setting them on collision courses with the planets. In Andromeda's more crowded stellar environment, these gravitational disturbances would happen more frequently, destabilizing approximately 30% more Oort cloud objects over geological timescales. This means Earth would face a steady increase in comet impacts, with the bombardment rate rising significantly above what we experience in our current galactic neighborhood. While individual comet impacts might seem insignificant compared to asteroid threats, the cumulative effect over millions of years could trigger more frequent mass extinction events. The beautiful stellar dome visible from Earth's surface would come with this hidden cost. Every spectacular night sky view would remind you that your planet sits in a galaxy where cosmic violence occurs more frequently, and comet impacts pose a persistently higher threat to long-term survival. But even Andromeda's dangers would pale in comparison to what awaits in galaxies where the night sky doesn't just glow with starlight, but burns with something far more deadly. The Quasar nightmare scenario. Now imagine living in WISE J22460, 526 plus 032 70652, one of the brightest quasars ever discovered, where the galactic core outshines 100 billion suns and bathes any planet within thousands of light years in lethal X-rays. This isn't your typical spiral galaxy filled with peaceful star formation and organized stellar neighborhoods. This is a quasar galaxy, powered by cosmic violence on a scale that transforms the entire galactic environment into something resembling the inside of a nuclear reactor. At the heart of this galactic nightmare sits a supermassive black hole weighing billions of times more than our Sun. That's roughly 1,000 times more massive than the black hole, sitting quietly at the center of our Milky Way. But mass alone doesn't tell the full story of why this galaxy would spell instant doom for Earth. This black hole isn't dormant like ours. It's actively feeding, devouring matter at a rate that creates the most violent and energetic phenomenon known in the universe. The galaxy's active galactic nucleus creates an environment where the central region alone outshines all the stars in the galaxy combined. Think about that for a moment. Every single star in this massive galaxy, from red dwarfs to blue supergiants, produces less total light than the glowing inferno surrounding the central black hole. The accretion disk, where matter spirals inward toward its doom, glows brighter than entire stellar populations. From Earth's surface, you wouldn't see individual stars at night because the galactic core would dominate the sky like a second sun that never sets. The real terror comes from what this feeding frenzy creates. As matter accelerates toward the black hole, it gets compressed and heated to temperatures exceeding several billion degrees. At these temperatures, atoms get ripped apart, and charged particles move at significant fractions of light speed. Active galactic nuclei accelerate particles to near-light speeds, creating cosmic death beams that extend thousands of light-years into space. These particle streams turn the galaxy into a massive accelerator where high-energy radiation floods every corner of space. Gamma rays, X-rays, and ultraviolet radiation stream outward from the galactic center at intensities that would make a nuclear bomb look like a birthday candle. Earth wouldn't just sit in a galaxy with these conditions. Earth would exist inside a cosmic microwave that operates at lethal power settings 24 hours a day, every day, for millions of years. The accretion disk around the central black hole operates like a cosmic blast furnace, heating and fouling matter to billions of degrees and creating X-ray and gamma radiation storms that propagate throughout the entire galaxy. These aren't brief bursts like the gamma ray events we occasionally detect from distant galaxies. These are constant, steady streams of deadly radiation that would bombard Earth's atmosphere continuously. Earth's atmosphere would begin disintegrating within centuries, rather than lasting the billions of years we have left under our current sun. The intense X-ray and gamma radiation would break apart nitrogen and oxygen molecules in the upper atmosphere, creating a cascade of chemical reactions that would strip away our protective atmospheric layers. The ozone layer would vanish completely within decades, leaving Earth's surface exposed to the full fury of the quasar's radiation output. But atmospheric destruction represents just the beginning of Earth's problems in this galactic environment. The gravitational chaos created by matter constantly falling into the central black hole would send shock waves rippling through the galaxy's gravitational field. These gravitational disturbances would affect stellar orbits throughout the galaxy, creating a cosmic environment where planetary systems face constant destabilization. The stellar population throughout the galaxy would also change dramatically due to the extreme radiation environment. Massive stars would have their lives shortened even further as intense radiation pressure strips away their outer layers. Stellar winds would become more violent and extensive, creating a turbulent interstellar medium filled with high-energy particles and electromagnetic radiation. Even at our current distance from the galactic center, roughly 26,000 light-years away, Earth would be positioned well within the quasar's lethal radiation zone. The inverse square law means radiation intensity decreases with distance, but the quasar's energy output is so extreme that even at interstellar distances, the radiation levels would be catastrophically high. Space missions would become impossible, as spacecraft electronics would be fried by radiation within hours of leaving Earth's magnetosphere. Satellites in orbit would fail rapidly as high-energy particles destroy their sensitive components. Radio communications would be disrupted by the constant electromagnetic noise from the galactic center, making long-distance communication nearly impossible. Ocean temperatures on Earth would rise dramatically as the planet absorbs increasing amounts of high-energy radiation. The water cycle would become chaotic as intense radiation heats the upper atmosphere, creating massive storms and weather patterns unlike anything in Earth's geological history. Ice caps would melt rapidly, not from greenhouse gases but from direct radiation heating. Living in this quasar galaxy means Earth's surface would receive thousands of times more deadly radiation than our current cosmic background environment. Every square inch of the planet would be bombarded with gamma rays, X-rays, and high-energy particles at levels that would sterilize the surface within months. The beautiful night sky filled with brilliant quasar light would be the last thing any Earth observer would ever see. But even this cosmic furnace of radiation and gravitational chaos would seem peaceful compared to finding yourself caught between two massive galaxies in the middle of a high-speed collision, where the very structure of space itself becomes a battlefield. Collision course in the Antennae galaxies. Picture this. You're sitting on Earth in the middle of two massive galaxies smashing into each other at 300 kilometers per second. The Antennae galaxies aren't just casually bumping into each other like two people in a hallway. They're engaged in a full-scale cosmic demolition derby, where 800 billion stars from both galaxies get flung around by gravitational forces, so intense they make our solar system look like a toy boat in a hurricane. This collision creates an environment where the basic rules of galactic structure go completely out the window. Instead of neat spiral arms and organized stellar neighborhoods, you get pure chaos. Stars that spent billions of years in stable orbits suddenly find themselves launched across intergalactic space at speeds that would make your head spin. The gravitational tug-of-war between the two galactic cores turns the entire system into a cosmic pinball machine, where stars are the balls and gravity provides all the bumpers. From Earth's surface, the night sky would display something that would make even the Andromeda scenario look tame. Massive tidal streams of stars stretch across 500,000 light-years of space, creating brilliant ribbons of light visible to the naked eye. These aren't subtle features you need a telescope to spot. These are cosmic highways of stars bright enough to cast shadows on Earth's surface. The streams curve and twist through space like enormous cosmic rivers, each one containing millions of stars that got ripped away from their home galaxies by the collision's gravitational violence. But here's where things get really dangerous for Earth. The gravitational encounters happening throughout this galactic war zone are so intense that they're launching entire stars completely out of the galaxy at incredible speeds. We're talking about stellar velocities that reach thousands of kilometers per second. These hypervelocity stars become cosmic bullets flying through space with enough kinetic energy to devastate any planetary system unfortunate enough to be in their path. Some of these ejected stars carry their own planetary systems with them, creating rogue solar systems that wander through intergalactic space. The collision triggers what astronomers call a starburst phenomenon, where star formation explodes to roughly 30 solar masses per year. That's about 10 times the normal rate you'd see in a quiet galaxy like our Milky Way. This means the collision is forcing gas clouds throughout both galaxies to collapse and ignite into new stars at an unprecedented rate. The result is a cosmic baby boom where massive, hot, short-lived stars get born in clusters throughout the collision zone. Here's the problem with all that rapid star formation. It creates approximately 10 times more supernovas than you'd normally expect in a stable galactic environment. Each of these exploding stars releases more energy in a few seconds than our Sun will produce over its entire 10 billion year lifetime. The collision zone becomes a cosmic fireworks display, where massive stars burn through their nuclear fuel in just a few million years before exploding in spectacular death throes. The supernova rate increase means Earth faces constant bombardment from high-energy radiation, gamma rays, and cosmic particles streaming out from stellar explosions happening throughout both galaxies. While individual supernovas might occur hundreds or thousands of light-years away, the sheer number of explosions creates a background radiation environment that would gradually strip away Earth's protective atmosphere over geological timescales. The collision disrupts the interstellar medium in ways that create additional hazards for our solar system. Shock waves from the galactic collision propagate through space at hundreds of kilometers per second, compressing gas clouds and triggering violent chemical reactions in the space between stars. These shock waves carry enormous amounts of energy and can travel across entire galactic regions, affecting star formation and stellar evolution patterns throughout the collision zone. When these shock waves reach regions near our solar system, they could compress local gas clouds to the point where they collapse and begin forming new stars. This process might sound harmless, but it could potentially create massive hot stars uncomfortably close to Earth. These new stellar neighbors would be blue supergiants with surface temperatures exceeding 20,000 degrees and luminosities thousands of times brighter than our Sun. The shock waves from the galactic collision could also destabilize our solar system's Oort cloud, that spherical shell of icy objects extending nearly a light-year from our Sun. Compression waves traveling through the interstellar medium would squeeze and stretch the gravitational field holding these frozen bodies in their distant orbits. This destabilization would send swarms of comets streaming toward the inner solar system, dramatically increasing Earth's chances of experiencing major impact events. The gravitational chaos extends beyond just flinging individual stars around. The collision gradually pulls the two galactic cores closer together in a death spiral that will eventually result in a merger. As the cores approach each other, they create increasingly violent gravitational disturbances that ripple outward through both galaxies. These gravitational waves would be strong enough to detect from Earth using sensitive instruments, providing a constant reminder of the cosmic violence happening at the galactic center. The merger process itself would create the most spectacular astronomical event visible from Earth. The two supermassive black holes at the centers of each galaxy would orbit each other with increasing speed and decreasing separation. When the black holes finally merge, they would release more energy in gravitational waves than all the stars in both galaxies produce in electromagnetic radiation. While the night sky would provide an incredible light show with brilliant star streams, constant aurora displays from high-energy particles, and the slow-motion spectacle of galactic merger, Earth would face a 200% increase in supernova-related extinction events compared to our current galactic environment. But all this cosmic violence and brilliant stellar chaos would seem overwhelming compared to a galaxy where the opposite problem creates an entirely different kind of nightmare. Lost in the darkness of Dragonfly 44. Dragonfly 44 presents the complete opposite scenario, where stepping outside at night would feel like being trapped inside a sensory deprivation chamber. This galaxy weighs roughly the same as our Milky Way, but here's the cosmic joke. You wouldn't be able to see any of it. The entire night sky would be almost completely black despite sitting inside a galaxy that contains the same gravitational mass as our star-packed home. The mystery of Dragonfly 44 reveals one of the universe's most bizarre configurations. This galaxy contains roughly the same amount of total matter as our Milky Way, which should mean hundreds of billions of stars lighting up the cosmic neighborhood. Instead, 99.99% of the galaxy's mass exists as dark matter, that invisible substance we can't see or directly detect, but know exists because of its gravitational effects. The remaining 0.01% of visible matter gets spread across only about 100 million stars, compared to our Milky Way's 400 billion stellar population. Those 100 million stars sound impressive, until you realize they're almost entirely aging red dwarf stars with surface temperatures barely hot enough to sustain nuclear fusion. Red dwarfs produce such feeble light output that even our closest red dwarf neighbor, Proxima Centauri, remains invisible to the naked eye despite being only 4.2 light-years away. Now imagine an entire galaxy populated almost exclusively with these dim stellar embers scattered across hundreds of thousands of light-years of space. Space navigation in this galactic environment would become completely impossible using traditional methods. Human civilization has relied on stellar navigation for thousands of years, from ancient Polynesian voyagers crossing the Pacific to modern spacecraft using star trackers for orientation. The Vikings reached new worlds by following star patterns across the North Atlantic. Without bright reference stars scattered across the night sky, these civilizations would never have developed the astronomical knowledge needed for long-distance exploration. The absence of visible stars would fundamentally alter human cultural development in ways that extend far beyond navigation. Astronomy wouldn't exist as a science because there would be virtually nothing to observe. Ancient civilizations built their calendars, mythologies, and religious systems around stellar patterns and celestial movements. The zodiac, constellation stories, and seasonal star cycles that form the foundation of human astronomical understanding would never have emerged in a galaxy where the night sky remains perpetually dark. The lack of massive stars throughout Dragonfly 44's history creates cascading effects that would make planets like Earth extremely rare or potentially impossible to form. Massive stars serve as cosmic factories that forge heavy elements through nuclear fusion in their cores. When these stars explode as supernovas, they scatter carbon, oxygen, silicon, iron, and other elements essential for rocky planet formation throughout the galaxy. Without massive stars, no supernovas occur, which means no stellar nucleosynthesis and no distribution of heavy elements beyond hydrogen and helium. This elemental poverty would affect planetary formation and chemistry throughout the galaxy's entire evolutionary history. Rocky planets require silicon, iron, magnesium, and other heavy elements that only form inside massive stars. Gas giant planets need solid cores made of heavy elements to gravitationally capture hydrogen and helium atmospheres. Without sufficient heavy elements, planetary systems in Dragonfly 44 would consist mainly of small, hydrogen-rich bodies that lack the complex chemistry needed for geological activity or atmospheric development. The biological implications become even more severe when you consider that life as we know it requires carbon, oxygen, nitrogen, phosphorus, and sulfur, all elements that form inside massive stars and get distributed by supernova explosions. Even if rocky planets somehow formed in this element-poor environment, they would lack the chemical diversity needed for complex organic chemistry. The absence of elements heavier than helium would make biological evolution virtually impossible. Dark matter's dominance in Dragonfly 44 creates gravitational effects that remain poorly understood by current physics. We know dark matter interacts gravitationally with normal matter, but we don't fully comprehend how such extreme dark matter concentrations might affect stellar orbits, planetary formation, or the behavior of gas clouds within the galaxy. The gravitational field created by invisible dark matter halos could produce unexpected tidal forces or orbital perturbations that affect how solar systems develop and remain stable over cosmic time. Our Sun's orbit within Dragonfly 44 would follow gravitational rules determined entirely by dark matter distribution, rather than the combined gravitational effects of hundreds of billions of visible stars. The orbital mechanics would depend on dark matter clumping patterns that we can't directly observe or predict. This uncertainty means our solar system's long-term stability would depend on gravitational forces we can measure but not see, creating an environment where predicting future orbital evolution becomes extremely challenging. Looking up from Earth's surface in this galactic environment, you might see our Sun, Moon, and planets, but the stellar background would appear almost completely empty. The handful of red dwarf stars scattered throughout the galaxy would appear as extremely faint pinpricks barely visible to the naked eye. Most nights, the sky would look like someone turned off all the lights in the universe. The eerie realization hits that Earth might represent the only significant source of light visible from its surface besides our Sun and Moon. City lights, lightning, and aurora displays would stand out dramatically against the cosmic darkness. In this galaxy, humanity would exist in complete cosmic isolation with no stars to dream about, no stellar destinations to explore, and no cosmic lighthouse beacons to guide future interstellar journeys. But what happens when you swing to the complete opposite extreme, where instead of too few stars, you face the overwhelming chaos of too many new ones being born at once? Surviving in a starburst galaxy. Welcome to M82, the Cigar Galaxy, where star formation operates like a cosmic assembly line running at maximum overdrive. This galaxy cranks out 10 solar masses worth of brand new stars every single year, which makes our Milky Way's leisurely pace of 1 to 3 solar masses annually look like it's barely trying. Living in M82 means Earth sits inside a galactic environment where stellar birth happens at such an accelerated rate that the entire character of space changes from a stable, predictable environment into something resembling a cosmic fireworks factory that never stops production. This incredible environment creates conditions where massive blue supergiant stars get born constantly throughout the galaxy's star-forming regions. These stellar monsters weigh 20 to 50 times more than our Sun and burn so hot that their surface temperatures exceed 30,000 degrees. They shine with the brightness of 100,000 suns, flooding their local neighborhoods with intense ultraviolet radiation that ionizes gas clouds across hundreds of light years. The galaxy becomes populated with these cosmic beacons that turn entire regions of space into glowing nebulae visible from incredible distances. But here's where the beauty becomes terrifying. These massive stars burn through their nuclear fuel so quickly that they explode as supernovas within just 3 to 5 million years after formation. In our Milky Way, stars like our Sun can live for 10 billion years, giving planetary systems plenty of time to develop complex chemistry and possibly life. In M82's rapid-fire stellar environment, massive stars barely have time to clear away their birth material before they detonate in spectacular explosions that sterilize everything within dozens of light years. The rapid stellar turnover creates a galaxy filled with young, hot, and unstable stars that exist in a constant state of cosmic adolescence. Unlike mature galaxies, where most stars have settled into stable, long-term nuclear burning phases, M82 remains dominated by stellar populations that haven't had time to reach equilibrium. These young stars pulsate, flare, and vary in brightness as they struggle to maintain stable nuclear fusion in their cores. Their erratic behavior creates an unpredictable radiation environment where energy output from nearby stars can fluctuate dramatically over short timescales. The stellar winds from these massive stars create phenomena that operate on galactic scales rather than just affecting local stellar neighborhoods. Each blue supergiant produces stellar winds that carry away material at speeds exceeding 2,000 kilometers per second. When you multiply this effect across thousands of massive stars throughout the galaxy, the combined stellar wind pressure becomes powerful enough to blow gas and dust completely out of the galactic disk and into intergalactic space. These galactic-scale outflows manifest as spectacular galactic fountains that shoot material thousands of light years above and below the galaxy's main disk. The fountains appear as enormous plumes of hot gas visible in X-ray and radio wavelengths, creating structures that extend far beyond the galaxy's visible boundaries. The material gets accelerated to such high speeds that much of it escapes the galaxy's gravitational pull entirely, never to return. The constant supernova activity throughout M82 creates shock waves that propagate through the galactic disk like ripples spreading across a pond. Each exploding star releases more energy in a few seconds than our Sun will produce over its entire 10 billion-year lifetime. These explosion energies don't just dissipate locally. They create expanding shells of superheated gas that travel at speeds of several thousand kilometers per second, compressing everything in their path and triggering chain reactions of stellar formation and destruction. These shock waves could trigger sudden star formation in our local stellar neighborhood, potentially creating clusters of massive stars within uncomfortably close distances to Earth. If shock wave compression causes gas clouds within a few hundred light years of our solar system to collapse and form new stars, we could find ourselves sharing cosmic space with blue supergiants that flood our region with deadly ultraviolet radiation. The formation of even one massive star within 50 light years would dramatically increase the radiation environment around Earth. The beauty of watching new stars ignite throughout the galaxy comes with the sobering realization that each newborn massive star represents a cosmic time bomb with an extremely short fuse. The brilliant blue light that makes starburst regions so spectacular to observe also signals the presence of stars destined to explode within just a few million years. Living in M82 means Earth exists in a galaxy where stellar death occurs at a rate roughly 50 times higher than in our current galactic environment. The mathematics of this stellar violence becomes staggering when calculated over geological timescales. While our Milky Way experiences roughly one supernova every 50 years on average, M82's accelerated star formation and rapid stellar evolution create conditions where supernovas occur approximately every year throughout the galaxy. The increased frequency means that over Earth's 4.5 billion-year history, our planet would have experienced roughly 225 million supernova events, instead of the 90 million that occurred in our actual galactic environment. The cumulative effect of living in M82's hyperactive stellar environment means Earth would face supernova explosions 50 times more frequently than in our current galaxy, making long-term survival nearly impossible for complex life forms. The constant cycle of stellar birth and explosive death would create a perpetual state of cosmic violence, where each generation of massive stars contributes to an increasingly hostile radiation environment that gradually sterilizes planetary surfaces throughout the galaxy. But what happens when you take the opposite approach and place Earth in a galaxy so massive that its sheer size creates entirely different problems for our planet's survival? The elliptical giant IC 1101. IC 1101 represents the ultimate galactic extreme, spanning 6 million light-years from edge to edge and containing roughly 100 trillion stars. To put that size into perspective, our entire local group of galaxies, which includes the Milky Way, Andromeda, and about 80 smaller galaxies, could fit comfortably inside this single galactic monster with room to spare. That's 250 times more stars than our Milky Way's 400 billion, creating stellar density variations that would fundamentally alter how our solar system interacts with its galactic environment. The galaxy's elliptical shape creates an environment completely different from the organized spiral structure we're used to in the Milky Way. Elliptical galaxies lack the distinct spiral arms that provide some gravitational shielding and organized stellar neighborhoods. Instead, stars distribute themselves in a more chaotic, three-dimensional pattern that follows the galaxy's overall elliptical profile. Our solar system would orbit through this environment without the protective structure of spiral arms or the predictable stellar density variations that come with organized galactic features. Without spiral arms to provide gravitational organization, our solar system becomes exposed to stellar encounters from all directions rather than just from neighbors in our local spiral arm region. The random stellar distribution means massive stars, stellar remnants, and entire stellar systems can approach from any angle, creating a much less predictable and more dangerous cosmic environment for maintaining stable planetary orbits over geological timescales. At the heart of IC 1101 sits a supermassive black hole weighing approximately 40 billion solar masses, making it roughly 10,000 times more massive than the black hole at the center of our Milky Way. This gravitational monster creates tidal forces that extend far beyond the galactic core, affecting stellar orbits and gravitational stability throughout enormous regions of the galaxy. The extreme gravitational field creates tidal forces strong enough to disrupt stellar systems that venture too close to the galactic center, stretching and compressing space itself in ways that can tear apart binary star systems and destabilize planetary orbits. IC 1101 represents what astronomers call a fossil galaxy, an ancient stellar population that formed most of its stars billions of years ago and has since evolved into a cosmic retirement community. The galaxy's stellar population consists primarily of old red giants and white dwarf stars, the elderly remnants of stellar populations that formed when the universe was much younger. This creates a dim, reddish galactic environment where the energetic blue and white stars that dominate younger galaxies have long since burned out and died. The lack of gas and dust throughout IC 1101 means almost no new star formation occurs anywhere in the galaxy. Young galaxies like our Milky Way contain vast clouds of hydrogen and helium that serve as raw materials for ongoing star formation. IC 1101 consumed most of its gas during ancient starburst episodes billions of years ago, leaving behind a galaxy where stellar birth has essentially stopped. The absence of young, hot stars creates a galactic environment dominated by the dim light of aging stellar populations. This ancient stellar environment would dramatically alter Earth's night sky appearance. Instead of the mixture of bright blue, white, and yellow stars we see from Earth, the galactic neighborhood would glow with the subdued red and orange light of aging giant stars. The overall brightness of the night sky would actually decrease despite the enormous increase in stellar population, because old red giants produce much less light per star than the younger stellar populations that dominate our current galactic environment. The stellar density near IC 1101's core reaches levels where individual stars regularly pass within a few light years of each other, creating an environment where close stellar encounters become routine rather than rare cosmic events. Computer simulations of stellar motion in the galaxy's central regions show that stars frequently approach each other closely enough to exchange gravitational energy, alter orbital trajectories, and potentially disrupt any planetary systems unfortunate enough to be caught in these stellar interactions. These frequent stellar encounters create a gravitational environment where the long-term stability of planetary systems becomes increasingly uncertain. Each time a star passes relatively close to our solar system, it exerts gravitational tugs on the outer planets, asteroid belts, and cometary reservoirs that gradually alter their orbital characteristics. Over millions of encounters spanning geological time, these cumulative gravitational perturbations could destabilize planetary orbits or even eject planets from the solar system entirely. The gravitational chaos from frequent stellar encounters also affects the Oort cloud, objects that orbit at the very edge of our solar system's gravitational influence. These icy bodies, normally stable in their distant orbits, would face constant gravitational perturbations from passing stars. Each stellar encounter would nudge some of these objects toward the inner solar system, dramatically increasing Earth's comet impact rate and creating periods of intense bombardment whenever particularly close stellar encounters occur. Binary star systems throughout IC 1101 face constant disruption as gravitational encounters with passing stars alter the delicate orbital balance between stellar companions. Close binary pairs might be torn apart by tidal forces from nearby stellar encounters. Wide binary systems could have their orbital separations drastically changed or their components completely separated. The high frequency of stellar encounters also creates opportunities for planets to be exchanged between stellar systems, with gravitational interactions transferring planets from one star to another. The cumulative effect of living in this ancient galactic giant means our solar system faces gravitational disruption, events at rates that make long-term orbital stability nearly impossible to maintain. Computer models suggest that planetary systems in IC 1101's environment experience stellar encounters close enough to disrupt orbital stability roughly 1,000% more frequently than similar systems in our Milky Way's more spacious and organized galactic structure. But even this chaotic environment of constant stellar encounters and gravitational disruption would seem orderly compared to finding yourself in a galaxy where the entire structure has been violently reshaped by cosmic collision. Chaos in the Cartwheel Galaxy. The Cartwheel Galaxy presents Earth with a cosmic crime scene where the evidence of galactic violence remains visible 200 million years after impact. This distinctive structure formed when a smaller galaxy, roughly the size of our Milky Way, punched straight through the center of a larger spiral galaxy at incredible speed. The collision wasn't a gentle merger but a direct hit that transformed a normal spiral galaxy into a cosmic bulls, with expanding rings of stars spreading outward like ripples on a pond. The smaller intruder galaxy barreled through the larger galaxy's center and kept going, leaving behind shock waves that continue spreading outward from the impact point today. These shock waves push gas and stars into expanding rings that currently span about 150,000 light-years across and continue growing at roughly 700 kilometers per second. The collision destroyed any organized galactic structure that existed before impact, scattering stellar populations into chaotic orbital patterns that follow no predictable rules. This expanding ring of star formation moves through the galaxy like a cosmic tsunami, compressing gas clouds and forcing them to collapse into new stars wherever it passes. The ring itself glows with the light of millions of newly formed massive blue supergiant stars, creating a spectacular sight that would dominate Earth's night sky. But this beautiful structure represents something far more dangerous than a pretty light show. It's a wave of gravitational chaos that triggers massive stellar birth followed by rapid stellar death, as the shock wave continues its outward journey. The starburst region at the galaxy's center forms stars at rates 10 to 20 times faster than our Milky Way, creating conditions where stellar death occurs at frequencies that would bombard Earth with deadly radiation regularly. Each wave of star formation creates a corresponding wave of supernova explosions that follow just a few million years later. These massive stars burn through their nuclear fuel rapidly, before exploding in spectacular death throes that release more energy in seconds than our sun produces over its entire lifetime. The supernova waves create additional shock fronts that propagate through the galaxy, independently of the original collision shock wave. Multiple shock waves from different sources intersect and interfere with each other throughout the galaxy, creating regions of extreme compression followed by regions of rarefaction. This produces an unpredictable pattern of stellar formation and destruction that makes it impossible to determine which galactic regions might remain safe from radiation bombardment. Living in this post-collision environment means our solar system would face the expanding shock wave if Earth happened to sit in its path. When this cosmic tsunami arrives, it would compress local gas clouds with enough force to trigger sudden star formation in our immediate stellar neighborhood. The compression could cause nearby molecular clouds to collapse and ignite, potentially creating massive hot stars within uncomfortable distances of our solar system. The shock wave's passage would send gravitational disturbances rippling through our local space environment, potentially destabilizing Oort cloud objects that orbit at the very edge of our solar system's gravitational influence. These disturbances could nudge thousands of icy bodies toward the inner solar system, creating comet swarms that would dramatically increase Earth's impact rate over the following millions of years. The collision destroyed the galaxy's original spiral structure and scattered stellar populations into highly eccentric orbits that don't follow organized patterns seen in stable galaxies. Stars throughout the Cartwheel galaxy move in chaotic trajectories that bring them into close encounters with other stellar systems much more frequently than would occur in a stable galactic environment. Binary star systems face constant disruption as ongoing gravitational chaos from the collision aftermath continues affecting stellar orbits. The collision created gravitational focusing effects, where material from both galaxies gets concentrated in specific regions, creating areas of extremely high stellar density separated by regions that remain almost empty of stars. Our solar system's position would determine whether we exist in a crowded stellar environment with frequent gravitational encounters, or in a cosmic desert with almost no nearby stellar neighbors. The ongoing ring expansion means collision effects continue influencing different galactic regions over timescales of hundreds of millions of years. The ring takes roughly 200 million years to cross significant portions of the galaxy, creating a cyclical pattern where different regions experience waves of intense star formation and subsequent supernova activity as the expanding shock wave passes through. The beautiful wagon wheel structure visible from Earth's surface would serve as a constant reminder of cosmic violence that shapes our galactic environment. Each spoke represents compressed material flowing inward toward the galactic center, while the outer ring marks the current position of the expanding shock wave. The entire structure continues evolving as gravitational forces from the collision aftermath reshape the galaxy's stellar population and gas distribution. Earth would face cyclical waves of stellar violence as ring expansion continues for hundreds of millions of years, creating periods of intense radiation bombardment followed by relatively quiet intervals as different shock waves pass through our galactic neighborhood. The unpredictable timing and intensity of these events would make long-term survival planning nearly impossible in a galaxy where cosmic violence operates on such massive scales and extended timelines. But even this organized chaos of expanding rings and predictable shock waves would seem structured compared to galaxies where no organizational principles exist at all, where stellar populations follow no rules and cosmic events happen according to pure chance rather than any discernible pattern. The irregular dwarf nightmare. The Large Magellanic Cloud represents the ultimate cosmic wild card, where chaos reigns supreme and organized structure becomes a foreign concept. This irregular dwarf galaxy operates like a cosmic free-for-all, where the basic rules of galactic organization get thrown out the window. Unlike our neat and tidy Milky Way with its spiral arms and predictable stellar neighborhoods, the Large Magellanic Cloud looks like someone took a normal galaxy and put it in a blender. Stars scatter randomly throughout space, without any clear pattern or organizational structure to guide their formation and evolution. The problem with existing in a galaxy that has no spiral arms, no clear rotation, and completely random stellar distribution becomes apparent when you realize that all the protective features we rely on in our current galactic home simply don't exist. Spiral galaxies like the Milky Way create organized star formation regions where stellar birth happens in predictable locations and follows established patterns. These organized regions provide some level of gravitational shielding and create stable stellar neighborhoods where planetary systems can develop without facing constant disruption from chaotic stellar interactions. Irregular galaxies lack these organized star formation regions that create stable environments for long-term planetary system development. Without spiral arms to channel gas flows and concentrate star formation into specific regions, stellar birth happens randomly throughout the galaxy in unpredictable bursts. This creates an environment where massive stars can suddenly appear in previously quiet regions of space, flooding their local neighborhoods with intense radiation and stellar winds that can disrupt any existing planetary systems within hundreds of light years. The Large Magellanic Cloud's interaction with our much larger Milky Way neighbor creates tidal disruption and stellar streams that make the entire galactic environment unstable over geological time periods. This gravitational harassment strips away gas and stars from the smaller galaxy, creating long streamers of material that get pulled toward the larger galaxy's gravitational influence. The tidal forces from this interaction stretch and distort the irregular galaxy structure, creating additional chaos in an already disorganized stellar environment. This gravitational harassment operates like cosmic bullying, where the larger galaxy constantly pulls material away from the smaller irregular galaxy, making it impossible for the smaller galaxy to maintain any stable structure over long time periods. Stars get ripped away from their original locations and flung into elongated orbital paths that carry them far from their birth regions. Gas clouds that could potentially form new stars get stripped away before they have time to collapse and ignite, reducing the galaxy's ability to maintain steady stellar populations. The lack of a massive central black hole means no organized galactic structure or predictable orbital patterns exist to provide stability for stellar systems throughout the galaxy. Unlike spiral and elliptical galaxies that have supermassive black holes serving as gravitational anchors at their centers, irregular galaxies operate without this central organizing force. The absence of a central gravitational engine means stellar orbits follow chaotic patterns determined primarily by local gravitational interactions, rather than the organized motion patterns you see in structured galaxies. Stellar formation happens in random bursts throughout the galaxy, rather than following the organized patterns seen in spiral galaxies, where star formation concentrates in spiral arms and follows predictable cycles. These random starbursts create pockets of intense radiation and stellar winds that appear in unpredictable locations without warning. A previously quiet region of the galaxy might suddenly experience explosive star formation that creates dozens of massive hot stars within a relatively small cosmic volume. These burst events produce massive blue supergiant stars that flood their local environments with deadly ultraviolet radiation and powerful stellar winds moving at thousands of kilometers per second. The radiation from these sudden stellar nurseries can sterilize planets within hundreds of light years, while the stellar winds create shock waves that compress surrounding gas clouds and potentially trigger additional star formation in neighboring regions. The unpredictable timing and location of these events makes it impossible to identify safe zones where planetary systems might develop without facing radiation bombardment. Navigation through space becomes nearly impossible in an irregular galaxy because the random stellar distribution provides no reliable reference points for determining position or direction. The constellation patterns that form the basis of stellar navigation in organized galaxies don't exist in irregular galaxies, where stars scatter randomly throughout three-dimensional space without forming recognizable geometric relationships that remain stable over time. The chaotic environment also affects the development of heavy elements needed for rocky planet formation and complex chemistry. Without organized stellar populations that follow predictable evolution patterns, the distribution of elements heavier than hydrogen and helium becomes random and unpredictable. Some regions might have abundant heavy elements from ancient supernova explosions, while other regions remain chemically primitive with insufficient materials for terrestrial planet formation. Binary star systems face constant disruption in the irregular galaxy's chaotic gravitational environment, where random stellar encounters can tear apart gravitationally bound pairs or alter their orbital characteristics unpredictably. The lack of organized stellar motion patterns means that close encounters between different stellar systems occur more frequently and with less predictable outcomes than in structured galaxies. Earth's survival would depend on cosmic lottery, luck rather than the protective features and stable environments found in organized spiral galaxies. The irregular galaxy provides no predictable safe zones or stable regions, where planetary systems might develop and evolve without facing constant threats from unpredictable stellar formation bursts, random supernova explosions, and chaotic gravitational interactions that could disrupt planetary orbits or strip away atmospheric protection through intense radiation bombardment. But what happens when you take this cosmic chaos and multiply it by factors that push stellar formation beyond anything we've discussed so far? What if Earth found itself in an environment where the very concept of extreme star formation gets redefined on scales that make even the most violent galaxies look calm by comparison? Phoenix Cluster's extreme environment. The Phoenix Cluster's central galaxy represents the absolute cosmic capital of star formation, where stellar birth happens at such extreme rates that it makes every other galaxy we've discussed look like they're barely trying. This galactic powerhouse cranks out 740 solar masses worth of brand new stars every single year, which is roughly 250 times faster than our leisurely Milky Way manages on its best day. Living in this environment means Earth exists inside a cosmic factory that operates at maximum production capacity around the clock, creating stellar neighborhoods that change dramatically over timescales measured in millions rather than billions of years. The entire galaxy sits submerged in a bath of 50 million degree plasma that extends throughout the surrounding cluster space. This isn't just hot gas floating around between galaxies. This is superheated material with temperatures that exceed the cores of most stars, creating an environment where normal matter exists in exotic states that don't occur anywhere else in the universe. The plasma glows with X-ray radiation so intense that it outshines entire galaxies when viewed through X-ray telescopes, creating a cosmic furnace that extends across millions of light-years of space. This superheated gas doesn't just sit there looking impressive. It actively rains down onto the central galaxy like cosmic precipitation, feeding both the supermassive black hole at the galactic center and providing raw materials that trigger the galaxy's explosive star formation rates. The inflow carries enormous amounts of hydrogen and helium directly into the galaxy's star-forming regions, where it gets compressed and heated until it ignites into new stellar systems. This process operates like a cosmic conveyor belt that continuously delivers fresh fuel for stellar formation at rates that dwarf anything seen in normal galactic environments. Step outside on Earth in this cosmic metropolis, and you'd witness something that would make every other galactic scenario look mundane by comparison. The night sky would display dozens of other galaxies as bright, clearly visible objects scattered across the stellar dome. These aren't faint smudges you need telescopes to detect. These are neighboring galaxies that appear as distinct, glowing structures visible to the naked eye, creating a cosmic city skyline where individual galactic components stand out like buildings in a downtown district. The cluster's high galaxy density means Earth's night sky would show spiral arms, galactic cores, and star-forming regions from multiple galaxies simultaneously. You could watch stellar formation happening in real time across different galactic systems, with some galaxies displaying the bright blue light of active star formation, while others glow with the steadier light of mature stellar populations. The visual effect would create a night sky so rich with galactic detail that finding empty space between cosmic structures would become nearly impossible. The extreme conditions create X-ray emissions from the hot cluster gas so intense they would generate aurora displays visible even during daylight hours. These aren't the gentle green curtains we occasionally see from Earth's polar regions. These would be brilliant, multicolored light shows that dance across the entire sky as X-ray radiation interacts with Earth's upper atmosphere. The aurora would appear as shifting sheets of blue, purple, and white light that remain visible against the daytime sky, creating a perpetual light show that never stops. But here's where the spectacular beauty transforms into existential terror. The extreme star formation rate creates an unprecedented number of massive stars, destined to explode as supernovas within just a few million years of their birth. With 740 solar masses of new stars forming annually, and roughly 30% of that mass going into stars massive enough to explode as supernovas, the galaxy produces approximately 220 solar masses worth of future supernova progenitors every single year. These massive stars burn through their nuclear fuel so quickly that the galaxy experiences supernova explosions at rates approaching one per month, rather than the one per century we see in normal galaxies. Each explosion releases gamma-ray bursts, X-ray radiation, and high-energy cosmic particles that propagate throughout the galactic environment. The cumulative effect creates a radiation background thousands of times more intense than what Earth currently experiences. The cluster's gravitational interactions become powerful enough to fling entire stars between galaxies like cosmic billiard balls. When galaxies within the cluster pass close to each other, Their gravitational fields can accelerate individual stars to speeds exceeding 1,000 kilometers per second, fast enough to escape their host galaxy entirely. These hypervelocity stars become cosmic projectiles that travel between cluster members, potentially carrying planetary systems along for the ride through intergalactic space. Living in the Phoenix cluster means existing in a cosmic metropolitan area, where extreme conditions represent the normal state of affairs rather than rare cosmic events. The high density of galaxies creates an environment where galactic collisions, stellar interactions, and radiation bombardment occur at frequencies that make survival planning nearly impossible. Each galaxy within the cluster affects every other galaxy through gravitational interactions, radiation exchange, and material transfer processes that operate continuously over cosmic time. The cluster environment subjects Earth to radiation sources from multiple directions simultaneously. X-ray emissions from the hot cluster gas combine with gamma radiation from frequent supernovas, ultraviolet light from massive star formation regions, and high-energy cosmic particles accelerated by magnetic fields throughout the cluster space. The cumulative radiation exposure creates an environment where atmospheric protection becomes insufficient to shield planetary surfaces from the constant bombardment. Earth would experience the most spectacular night sky imaginable, with galactic structures, aurora displays, and stellar formation regions creating a cosmic light show that operates on scales impossible to comprehend from our current galactic neighborhood. But this incredible beauty comes with radiation levels approximately 100 times higher than normal, creating an environment where the magnificent views would be the last thing any observer would see before succumbing to the extreme cosmic conditions. After exploring all these galactic extremes, from Andromeda's stellar density to the Phoenix cluster's radiation furnace, you might think we've covered every possible scenario for Earth's survival in different cosmic environments. But recent astronomical discoveries have completely changed how we understand these galactic dangers and opportunities. The James Webb Revolution. The James Webb Space Telescope has completely flipped our understanding of how galaxy swaps would actually affect Earth's chances of survival. Everything we thought we knew about galactic habitability just got thrown out the window, thanks to breakthrough findings that reveal how galaxy environments affect planetary atmosphere retention over cosmic time scales in ways we never imagined possible. The game changer comes from James Webb's ability to peer deeper into galactic structures using infrared wavelengths that reveal hidden features invisible to previous telescopes. The telescope's advanced deep extragalactic survey captured approximately 2,500 visible galaxies in a single field of view, with 4/5 of them being distant, high redshift galaxies that show us what galactic environments looked like when the universe was much younger. These observations revealed that galaxy types we thought were rare actually dominated the early universe, completely changing our calculations about which galactic environments might support long-term planetary survival. The infrared observations uncovered galaxy types that weren't even known when scientists first started imagining these galactic swap scenarios. James Webb identified dozens of small starburst galaxies that punch way above their weight when it comes to producing ultraviolet radiation. These tiny galaxies, which make up only about 1% of galaxies around us today, were abundant when the universe was about 800 million years old. The discovery means our galaxy swap scenarios need completely new categories for these hyperactive stellar environments that create radiation conditions, unlike anything in modern galactic populations. James Webb's infrared vision revealed hidden structures in galaxies that fundamentally change survival calculations for planets in different galactic environments. The telescope detected strong emissions from oxygen atoms that have lost 2 electrons, which indicates high-energy processes happening throughout these early galaxies. This green line emission, stretched into infrared wavelengths by cosmic expansion, shows that even small galaxies can create extreme radiation environments that would affect planetary atmospheres across much larger volumes of space than previously calculated. The data shows that galaxy mergers happen more frequently and violently than earlier models predicted. Webb's observations of colliding galaxy clusters like the Bullet cluster revealed the collision process strips away protective gas halos and exposes planetary systems to cosmic radiation in ways that make survival much more difficult. The telescope's detailed mapping shows how dark matter gets redistributed during galactic collisions, creating gravitational chaos that affects stellar orbits and planetary system stability over much longer timescales than scientists previously understood. New measurements of supermassive black hole masses from Webb observations completely change the radiation danger calculations for different galaxy types. The telescope's infrared capabilities allow astronomers to study black hole accretion processes in unprecedented detail, revealing that many galaxies contain black holes significantly more massive than earlier estimates suggested. These revised mass measurements mean radiation levels in galaxy types like quasars and active galactic nuclei create lethal zones that extend much farther from galactic centers than previous models indicated. The most shocking discovery involves dark matter's role in either protecting or exposing solar systems to cosmic threats. Webb's observations of gravitational lensing, effects in galaxy clusters, show that dark matter distributions create protective zones where stellar systems remain shielded from high-energy radiation sources. But the same dark matter concentrations can also channel cosmic rays and particle streams into focused beams that create radiation hotspots throughout galactic environments. This means galaxy choice affects planetary survival through dark matter interactions we're only beginning to understand. Updated stellar population models based on Webb observations reveal new dangers and opportunities in different galactic environments that nobody saw coming. The telescope's ability to analyze stellar populations in distant galaxies shows that star formation rates fluctuate much more dramatically over cosmic time than scientists realized. Galaxies that appear quiet and stable today might have experienced violent starburst episodes in their recent past that created lingering radiation environments hostile to planetary atmospheres. Webb's discovery of extremely faint and distant galaxies in regions like the Bullet cluster shows that galactic neighborhoods contain many more radiation sources than previous surveys detected. These newly discovered galaxies contribute background radiation that affects atmospheric chemistry on planets throughout cluster environments. The cumulative radiation from multiple faint galaxies can create hostile conditions even when no individual galaxy appears particularly dangerous. The infrared observations also revealed that stellar winds and outflows from star-forming galaxies extend much farther into intergalactic space than anyone expected. These galactic fountains of high-energy particles create radiation streams that can affect planetary systems in neighboring galaxies, meaning galaxy choice involves considering not just your home galaxy, but the entire galactic neighborhood surrounding it. James Webb's measurements of interstellar dust distributions show how galactic environments affect the delivery of heavy elements needed for rocky planet formation. The telescope revealed that dust clouds in different galaxy types contain varying concentrations of silicon, iron, and other planet-building materials. This means some galaxy types might actually provide better conditions for terrestrial planet formation, despite having higher radiation backgrounds from active stellar populations. The breakthrough finding that changes everything is Webb's detection of atmospheric signatures from exoplanets in different galactic environments. Early results suggest that planets in certain galaxy types develop atmospheric chemistry that provides better protection against cosmic radiation than Earth's current atmosphere. Some galactic environments might trigger atmospheric evolution that makes planets more resistant to radiation bombardment rather than more vulnerable. The most revolutionary discovery involves galaxy types that might actually offer better habitability conditions than our Milky Way. Webb identified galaxies with stellar populations that produce lower background radiation levels while still maintaining active star formation needed for heavy element production. These galaxies have organized spiral structures that provide gravitational shielding, combined with stellar populations dominated by long-lived stars that create stable radiation environments over billions of years. The telescope's ability to study galactic chemical evolution in unprecedented detail reveals that timing matters more than galaxy type when it comes to planetary survival. Webb shows that most galaxies go through phases where conditions become either extremely hostile or surprisingly habitable, depending on their stellar formation history and interactions with neighboring galaxies. These revolutionary infrared observations have changed our understanding of how galactic environments actually affect planetary survival over cosmic time. The science from James Webb suggests that galaxy choice represents the ultimate factor determining a civilization's cosmic longevity. But the decision involves much more complex calculations than anyone realized. After exploring all these cosmic environments and their hidden dangers, we're left with one unavoidable question about our own galactic home. The calculations reveal something remarkable about our cosmic address. After traveling through quasar death zones, galactic collisions, and dark matter prisons, one thing becomes crystal clear. Our Milky Way might be the cosmic equivalent of winning the galactic lottery for habitability. We hit the jackpot with organized spiral arms, stable star formation rates, and a supermassive black hole that stays quiet instead of blasting us with deadly radiation. Galaxy choice determines everything from whether civilizations develop astronomy to whether planets keep their atmospheres for billions of years. So next time you look up at our relatively peaceful night sky, remember that we're living in one of the universe's rare safe neighborhoods.